Hi there. I want to share with you some demonstrations regarding the Pearson test and the t-test. So let me start by sharing my screen with you. We'll start with the Pearson test because this is the most awkward one to fully do in Excel. And it's simply because the inbuilt function isn't as thorough as it might be. The t-test, when we'll come onto it, is far more straightforward. Let me just explain where these tests lie in the grand scheme of things. This is an example of what's known as a flow chart, a decision chart, to help us decide which test we might use, which inferential test we might use in analysing our data. Inferential tests, you'll remember what we do after descriptive test, after our mean, median, mode, standard deviation, that kind of thing. Now, this decision chart tells us that if we're looking, say, at just categories, we'll look at the chi-square test. And categories means that we have data that's only what's known as nominal level or categorical level data, things where you can categorize them and do counts, but nothing more. Sometimes, and you'll have seen this at school, where we might do scatter plots across two variables. And that's where we're looking at something called correlations. There are two types of correlation tests. One we'll do today, the Pearson test, and there's another one called the Spearman test. Now, this little phrases above it, power and non-power, we shall see across quite a few of these tests are referring to the quality of the data. If your data is what's known as parametric, then it's to have the highest quality. Now, parametric data has to fulfill four justifications. One is that the data must be at interval or ratio level data. The hierarchy of quantitative data types has nominal level data at the bottom, categories, and then ordinal level data where you might ranking. You might have questionnaires that ask you to strongly disagree, moderately disagree, neutral, agree, strongly agree. That's known as Likert type data, Likert type variables, and from that we get ordinal data. But above those two, a much higher quality data called interval and ratio, where effectively they are measures that do what they say on the tin. They are interval level data is where you might have an arbitrary zero, like degree centigrade. Ratio level data might be where you have an absolute level of zero, for example, degrees Kelvin. But suffice it to say, if your data is interval or ratio, if it appears you're measuring something real numerically, then it passes that second test. The third test for your data to be considered parametric is that the data or the measure of the variable that you're taking clearly as a sample has to come from a population that itself is normally distributed. Remember that nice symmetric bell curve type shape that you might get. Now, your sample may not demonstrate that same shape, but that's simply because you've got a low-ish sample size. If you know from other studies that the population samples were taken with a much greater sample size shows that distribution, then you can say it is normally distributed. And the fourth and final condition for your data to be considered parametric is that across your two or more groups, they have to have similar variances. Now, the variance is another measure of spread. It happens to be the square of the standard deviation, and that might seem quite a game changer, but certainly at least three of those four categorizations have to be are considered to be robust in that you can move quite a long way. I've not mentioned that your data, final one, I'm not mentioning your data must be continuous and not discrete. Discrete data is like whole numbers, how many children in a family, how many teams in the premiership, whereas continuous data is where, as an act of measurement, you can go ever more precisely. I've given those out of order, but there's not necessarily an exact order. Suffice it to say that parametric data is the highest quality. If you're not sure that your data is of the highest quality, then you should go to the non-parametric test. But there are lots of ways of ascertaining if your data is of the higher quality. So we can see from this flow chart, and I'll come back to this when we look at the t-test, that if we're considering doing any measurements on correlations, and we consider that our data is likely to be parametric, then it seems reasonable to run the Pearson correlation test. So that means we expect to see some scatter plot like this, where you can imagine a straight line cutting through the two. Now, the correlation itself, the strength of the correlation, is given by a correlation coefficient, a number that can go anywhere between +1 and -1. If it's +1, then it is what's known as perfectly positively correlated. -1 will be perfectly negatively correlated, and our value, a correlation coefficient value close to 0, would indicate that there is no association, there is no relationship between your two variables. And typically, if you're in the 0.8 or -0.8, you could consider it to be a strong correlation. Around 2 would be considered weak, and around 0.5 would be considered moderate strength. So, first thing you should always do when considering doing a correlation test is you must visualize your data. So here's an example of the data set that you've been given. So I want to just visualize the data. So I'm just going to do, as an example, say before one versus after one for the whole data. So I'm mixing up men, women, I'm mixing up device A and device B, but this is just for illustration. So I'm going to click and hold, and to make life easy for myself, I'm just going to do the first 20 because I can't be bothered to do all of them. Okay, so I've held that, and now to get this next one, I must hold the control key down so it doesn't forget my first measurement. So I've been careful to pick the first 20 data points for, in this case, the rater number 1, and they're before versus after. And I would expect there to be some correlation between the two. You're now going to insert at the top. You're looking for our charts, and we're going to pick that top left one, the scatter plot, and there it is. And you can see, not as clear as I might, but you can see that there is a positive correlation. It slopes upwards as you go left to right. Now we can make this a little bit clearer by just right-clicking on these axes and just making them a little bit nicer. I've noticed that nothing goes below 5, so I'm going to make my minimum, say, 5. Hit return, and that's helped spread out the x-axis. I want to do the same with the y-axis, so we'll go to the y-axis, right-click, and select format axis. And now here I note it also doesn't go below 5, so say 5 is my minimum, and my maximum I'll leave as 10. And now you can see that we've spread out our data in order for us to see, to evaluate, just eyeballing the data, whether there is or is not an apparent correlation. And there seems to be. In fact, I could imagine putting a line of best fit, going from the lower left to the top right, that would pretty much capture the shape. And it does appear to be linear meaning a straight line. Non-linear ones are ones that we're not going to cover and worry about in this particular part of the course. Okay, now that I've convinced myself that there seems to be a correlation, let's see what Excel has to offer. So now I think Excel is going to be awkward here. So what I'm going to do is I'm just going to, well, let's go into Excel. I'm going to go into data. I'm going to pick data analysis. Now, if you're doing this yourself and you said, hang on, I'll click data and there's no data analysis button, it means you haven't installed the data analysis package. Not a problem. You would go down to File, go down to where Option is. In my case, it's right at the very bottom. You click on where it says Add-ins on the left-hand side, and then go down to the bottom. Make sure that Excel Add-ins is selected and click Go. In fact, I think I click Go. Okay, let's find out. Click Go. Yeah, and you notice I've already selected those packs, the top 2. The top one's most important, but when I saw a video on this, it said select the top 2. Then you click OK. This then should magically appear. If it doesn't, and I've saw one example in class where it didn't, then what you do is you come out of Excel, relaunch it, and the time we saw that it did then magically appear. So we want to see what Excel has to offer in terms of the Pearson test. So back to where I was at, click on data analysis. It's got correlation. That sounds reasonable. Click on that. Click OK. And it says, OK, what is your input range? Now, yes, I've just realized where this goes a little bit wrong, because if I want before 1 and after 1, and I try and do is say the first 20, let me show you what happens as a mistake, or limitation rather. I've clicked the first one, hold the control key down for after 1 to try and do what I did before. So I'm hoping that was OK. And because I kept the labels in, I'm going to click on labels. For my output, I'm going to say it's going to go, say, click into there and then say, put it there, please. And I think it's about to go wrong. Yeah, it does. It says your input range must be a contiguous reference. I've tried no end of dead ends on solving this. So what I'm going to do to solve it is to say, well, it must allow me to do it. I'll just click cancel on there for a second. I'm going to copy the whole thing. So I've selected top left, use Control C to copy. I'll open up a brand new sheet, so I'm not messing things up. Always a good habit to do this anyway is to make copies of your raw data so that you're not If you make any mistakes or anything, you can always go back to the raw data and make a new copy. Now, I want before one and after one, so I'm just going to get rid of that row and that column. So, and it's okay that I've done that because I'm not, I've got my original to go back to. So now let's go back to data analysis, select correlation, hit OK, get rid of that particular line because we know now that's wrong. And now I want to do before one and after one. I'm including my top row, which is my variables. Obviously, when you do this, you'll do the whole of the data. I'm just doing the first 20 because I'm being lazy. Got my labels in the first row ticked because there are indeed labels in the first row. My output, I'll just rub that out and make sure it goes somewhere sensible. So put it, say, there, click go, cross my fingers. Phew, we've got something. So the Excel data analysis package for correlation only gives you, it's important, but it only gives you one value, which is the correlation coefficient. And you can see that for that particular scatter plot, it's calculated, and this was a Pearson test, by the way, it doesn't say it out loud, but it is. The correlation coefficient is 0.944, very close to +1. So you might say there is a very strong positive correlation between for rate of 1 in the measure of agility after versus the measure of agility before. So you might say that. I've got a problem with this, and that is I need to know more information. Excuse me. I want a t-test. Sorry, I want a p-value, I beg your pardon. I know for this to be an inferential test, I not only want to record what was the strength of the correlation and obviously comment upon that, but I want to say something about whether it was genuine or could it have occurred by chance. Now we can see, looking at this, very unlikely to have occurred by chance, but we're playing a numbers game here. We're trying to get the greater level of marks for our reports, and we've got to fill in all the details. So Excel, as the data analysis package, did not permit us to do it. What to do from here? Well, now we go to the notes, and we are given some information. We're going to have to do it, as it were, by hand. We don't mean a pen and paper or even calculator, because Excel itself permits us to insert formulas, either ones we've made up or ones that are inbuilt. So there are inbuilt formulas in Excel, as well as inbuilt elements of data package, the analysis package. They're two different things. And what's going on is that we'll work out the R value, which we do already know, but we'll keep going. And then we have to just to look ahead. We've then got to work out the p-value from the distribution that the Pearson test relies upon. The Pearson test relies on, believe it or not, the t distribution, and it's how far along the t distribution. You can already see how difficult this is getting conceptually, but it will just come down to clicking buttons. Let us remind ourselves of what a t distribution is. That is the formula for the t distribution, but I think it's far better just to look at it visually. Now, I found this on web. You'll see that the t distribution, well, for one thing, there's more than one. There's what's known as a whole family of t distributions. They're all unimodal and they're all symmetric. They all fall away symmetrically either side of the mean. This particular example that I stole from the web happened to have a mean at 0, but whatever your mean was. Now, look at this thing called the degrees of freedom. The red curve was for a t distribution with 10 degrees of freedom. For 20 degrees of freedom, it became a little pointier. And then that black one, it says a t distribution with an infinite degrees of freedom. In other words, as a very large number for your degrees of freedom. And that t distribution with a very large degree of freedom is identical to a standard normal distribution. You can see already there are hints of these undercurrents, these similarities, these relationships between various statistically mathematical distributions. Okay. Whichever distribution we have, we know that if we have a value which is larger than some critical value, in other words, in this tail region, in the small part of the tail region, then we are likely to be able to declare statistical significance. That's why we have to calculate a t statistic, what they're calling a t-stat, and then we would look either in lookup tables or here in Excel, they have built-in lookup tables, and they will tell us if that t-stat exceeds some critical value for which we can then declare statistical significance. Okay, so go back to my data. I want to do a bit more work on this. So the degrees of freedom is nothing more than just the number of values in my data minus 2. Okay, let's start with this. So I'm going to work. I'm just going to see if I can get that same R value. So R equals, now this is not a formula, this is me labeling. I'm going to go use the tab key to go to the next cell. Whenever you start a cell with the equal sign, then Excel knows we're working in formulas, and up this top left you can often look things up, but I know it's called Pearson, so I'll just start typing in Pearson, and there it is. It recognizes the formula I'm trying to do, so I'm going to double click on that, and then it sets it up correctly. It tells me it needs 2 arrays, array 1 and array 2. Now, I'm not sure if I'm allowed to include the labels. I'll try it with the labels and without. And again, I'm going to just do the first 20. I'll leave you to do it on the first full one. It wants a comma, and then it says array 2, please. And again, I'll do it with the labels. If it doesn't work, I'm just going to go back and do it without the labels. And it needs me to close the formula, and then it's disappeared, which means it's now happy with my what's known as syntax setting up. And I can either click tick to say I'm ready, I'm done, or I can hit return. Now, at the moment, this cell has just got a formula in there, but when I hit return or click the tick, it comes up with a number, and huge sigh of relief, it gives me exactly the same correlation coefficient that we got with the pull down. Okay, fine. I'm just plowing through this step at a time just so we can make sure we know what we're doing. We need the value of R because, why do we need the value of R? Because in that formula for the T distribution, R occurred in it, both in the numerator and the denominator. Okay, what do we need to do next? Well, we need to know N, which is the count, and it's just a count in one of the columns. So I'm just going to put here N equals, and then go over here and put equal sign again to let Excel know I'm doing a formula, and there is a inbuilt formula called count. So there it is, count, top one, and it just says it counts the number of cells. So if I know it's 20, but I'm doing this if I had a large data set, I'm just going to select the first 20. It says okay, close, hit return 20, happy so far. And then the degrees of freedom for this particular test is defined as n-1, the number of counts minus 1. Okay, so go over to here, and I could just say equals 18. Of course I could, but I might as well follow it through and do equals n, because I clicked on that cell that had an answer, which has come up as an address, as it were, the cell number I23, minus 2, hit return, and I get 18. It's worth doing it this long-handed way, because when your marker looks at your report, and in addition to the report, you'll almost certainly have to upload your Excel spreadsheet. The marker can then look to see what you've done in each case. Otherwise, you could just write down the number 0.944, or just write down the number 20 or 18 and not demonstrate that you have correctly followed the steps. Okay, so far so good. We are now at a point where we can calculate the Pearson the Pearson correlation T statistic. Now let me just go down a little bit and remind ourselves what it looks like. It says T equals, and then this formula, R times root n minus 2, that's a square root, divided by square root of 1 minus R squared. We have all that information, so, and we're going to call that the T stat. So this is where it gets fiddly, and I always make mistakes. So I'm just going to put here T stat equals, and again, that's just my label. It's not until I go to this cell that I'm going to start putting it in. So equals, and then it was R times, now R is this value, times, in Excel you use the star, which is above the 8, so I did shift 8, and then it is going to be, now I want to put here the square root of n minus 2, so I'm just going to open a bracket and put sqrt, which is going to be the square root of, I've just double clicked, of a number, well it's the square root of n minus 2. Well, n minus 2 is just degrees of freedom, so let's put that in there. Close bracket. I've just realized this. No, I have not made a mistake yet. Divided by over, and then square root again, sqrt. Double click on that one, and then it's 1 minus R squared, 1 minus, and then where is R? It's this value here. And to put squared, you do Control-6, which is that little caret sign, and 2. And that means raised to the power of 2, in other squared. Close the bracket, and at the moment, have I closed all my brackets? No, I haven't, because there's that initial bracket that I have to now close again. And you notice how they color code it, which is quite useful. It lets you match up and make sure that you're not missing anything out. I think we're okay. Let's see what we get. We get the answer 12.1454. Not that means anything to me. It just seems like a large number. I know from the back of my mind that if this was the normal distribution, the critical value of the what's known as the Z value, the number that determines the normal distribution, that is something like 1.96. I only did a sample size because I was lazy of 20, so you might think, okay, it might be broadly speaking similar value, so I think 12 is going to be much larger. I'm fairly optimistic here. Now to get the p-value, so let me label it as p-value, just so my report looks nice and neat. Let's just remind ourselves on the slide how we work out the p-value. Okay, the p-value is where we call up another Excel function called tdist. This is like the lookup tables, and it's tstat, comma, degrees of freedom, comma, 2, and basically it's referring back to the tables that go with whichever t distribution, whichever member of the family, and it's going to compare it with the critical value. Okay, so find ourselves again what it looks like. Tdist, tstat, df2. Right, back to my slides. So p-value equals, I'm trying to do a formula, and I want to do tdist. Let's see if it recognizes it. Yes, I just put tdis. It recognizes it. Double click. Okay, it wants x, which is my tstat, which is this value here. Then it wants a comma. Then you notice how it goes in both phases to saying what it wants next. Degree of freedom, which we've already worked out, this value. I'm only clicking once every time I select one of those. Click comma and then tails. Well, what's this all about? If I put 1, it's a one-tailed distribution. If I click 2, it's a two-tailed distribution. Let me put 2 and close it and just hit return. And before I investigate that, any distribution that's symmetric, like the t distribution and the normal distribution, because it's symmetric, you can have this concept of the one-tailed test or the two-tailed test. You would nearly always run the two-tailed test. It's where you know for sure if your data can only move in one direction or might move in either. If I'm looking at, say, the use of something to help with agility, like mechanism 1 versus mechanism 2, I won't know which is the better one. So I'm going to have to run a two-tailed test. Even though I might be hopeful or very hopeful there can be one better than the other, it's more honest to run a two-tailed test. The only example I've come across where you would run, say, a one-tailed test is if you're looking at children's language levels, say between the ages of 4 and 5. And you've got, say, children where they have a mild speech and language disability, and you have a speech and language therapist with some new innovative intervention. Now, we know that between ages of, say, 4 and 5 or 4 and 6, we know that regardless of any intervention, their language is going to improve because that's how children are. Obviously, what they're wanting to know is, does their intervention work better than just natural maturation? So in their case, they would have a strong case for saying a one-tailed test. In your case, go with two tails. That's why I picked 2 for that. Go back and see what we got. So we're not told the critical value, never mind, and maybe that's possible somewhere, but the p-value is definitely less than 0.05. Because what they've given here is they've given a curious way of writing a very low number, a very small number, known as scientific notation or exponent notation. And that reads as 4.156 times 10 to the minus 10. In other words, 0.00009 zeros 415. In other words, we can say rather that p is very much less than 0.05. I've just written that in to remind myself. I can say that we have very strong evidence against the null distribution. I've just made a note for myself to say fine. So we've now completed the full version of the Pearson test that our markers would want us to do. We produced a visualization which allows us to comment in our writing about how there appears to be a positive correlation for before versus after, and I might label these axes. I've not worked out to do that. We used their inbuilt test, which only gives us a certain amount. That would not give us full marks. That helps. It tells us what the correlation coefficient is, but it doesn't give us a final value. So I then had to go down this rabbit hole of saying, okay, how am I going to work this out? Because of that formula of the t distribution value being r n minus 2 over all that lot. It then meant I had to go down the road of then working out the value of t once I had got these numbers in place, and then I used the what do they call it, the tdist. It's like an inverse function, the tdist function, to work that out. Okay, fine. We completed the Pearson test. We're halfway through. This last part will be nice and quick, which is the t-test. And by the way, when you're running your distributions, you're not just going to look at before one versus after one and just rater number one. You might want to look at rater number one and rater number two. Your initial discussion of deciding whether rater number one and rater number two are equivalent, you might run a Pearson test of before one against before two. You might want to expect and say, I expect there to be a near perfect positive correlation between before one and before two, etc., etc. So there's always a deeper dive you can do, and there's always more variables you can look at. Don't just analyze all variables against all variables for its own sake. Do have a logic behind it. Do allude to something like this flowchart to justify why you're doing your test, what you're trying to show, what your null hypothesis is, and whether a rejection of the null hypothesis means one thing or the other. You've got to be careful with that. Okay, final thing to do is t-test. So while we keep on this particular flowchart, a t-test is one of the more simpler tests of differences across two groups. If you have more than two groups, then you're looking at what's known as an ANOVA test. So if I'm looking at a test of differences and I've got one variable, say the level of agility. So I'll go down this one here and it says, how many experimental conditions have you got? Well, if I've got only two, like group A, group B, I'll go down this road. And by the way, two groups could also be the same group measured before and after, because the group before at baseline, you consider that a group, and then after the intervention, in a very real sense, they've kind of changed. You see them as a separate group, group two. So go down this 2-1 and then say, okay, was it within or between group study? Well, a within group study is classic before after. Between is group A versus group B. I'm going to think about this. Certainly with our data, we have an opportunity to do both. So either way, we're going to consider what's called the t-test related, sometimes known as a paired values t-test or the dependent t-test. Then you've also got your t-test unrelated, also known as the unpaired t-test, also known as the independent samples t-test. Bit of a mouthful, but you can see what's going on. If our data was not parametric, there are tests available, and it would be big fingers crossed and pray to whatever God you have as to whether there is going to be a pull down package within Excel for that. But we're going to go with t-test, which I know for a fact has got a package for us. So back to my data. I'm looking at my raw data now. Let me just find, here we go, this one I want to look at. So look at my this one. Now this one I'm looking at the t-test of differences. So at the moment there's pretty much no change. What have I changed from the beginning? I'm not sure I've changed very much. I've taken out the patient number, which was just a label, but I think I've kept everything else. Gender device, is that right? Have I kept everything else? No, the device is gone. So what I've done is I've selected. So what I did, let me just go back here. I want to go to my got an example somewhere of all the data. Maybe it was on the Pearson. Yeah, it was here. So let me just copy this, put up a new one. Okay, and I'll get rid of this. Don't want that anymore. And also I won't want that top line anyway, so I'm just going to delete that line. I don't need the patient number, and you can see I'm being quite cavalier here because I just want to trim it down to what I need. Now I'm going to leave it as that and say I'm going to do a t-test of differences, and it doesn't really matter which one I do. So here we are. I'm going to look at, say, a difference between, say, before one and after one, for example. This part is really, really quick. We know it's a t-test, and let's think about it. Pause the video if you want to decide, am I looking at a within group study, before versus after, or am I looking at independent samples? I'm looking at that column before one and after one. Which one do you think I'm going to be using, the paired or the non-paired? Well, in this case, it could be the paired. If I was comparing before one and before two, they're independent. I would then go for the independent samples. So click on data, click on data analysis. Got lots of different examples. It's got the t-test paired, that's what we're going to use. It's also got t-test 2 samples, assuming equal variance, and t-test 2 sample, assuming unequal variance. We'll come back to that one, but let's pick the paired one for now. Click OK, little pop-up box appears, and it's got 2 boxes, and because there's a box there that says for labels, I know I can keep the labels. So let's compare before one versus after one. So again, I'm going to be lazy and just pick the first 20. That's that one. Click in that box. Now do after one, and don't just click on that top row. I don't want to do that because I know it'll muck things up. We tried this in class and it went a bit wrong. Okay. Your hypothesis mean difference. Well, a mean difference would be after, take away before. So if they were the same, your null hypothesis would be 0. Some tests and some measures look at a ratio. So if you have the same number over itself, then the null hypothesis value would be 1. But here it's 0. I do want the labels including. This alpha is our significance level. And what that means is, are you going to be adopting the common value of 0.05, which means you interpret p-values less than 0.05 as being statistically significant? The answer is yes, but there are occasions when sometimes you want to make that more stringent, like with very, very expensive drugs or very harmful drugs like chemotherapy. So output range, click on there to let me know where I'm going to put it there, please. And now I'm pretty much all set to go. Click OK, and everything is done for me. So there was no input on my front in terms of formulas and distributions and all that kind of thing. So I'll make things a little bit tidier. Certainly I don't want all of these decimals, so I'm not going to select them all. If I go back to home, I showed this in class where you can just reduce the number of decimals. I'm going to stick to say 3 decimals. I think as long as you're consistent, 2 or 3 should be enough, but you might want to talk to your program leads. Now here, I'm going to be careful because if I start fiddling around the number of decimal places on these E numbers, you might start getting a bit weird. So I'm just going to make sure I don't include them in this tidying up exercise. I'm only doing this so that when I cut and paste into my report, I'm fairly happy. You'll notice that it gives a p-value for 1-tailed test and a p-value for 2-tailed test. Now you might keep this data in your report and talk about why you are not using the 1-tail and why you're picking up the 2-tailed, or you might say, look, it's too much information, I don't want this, so I'm just going to select that, click delete when it says shifts cells up. Yes, I think it was okay there. I think it's because it didn't want to rub out the actual values. But look at what we've got. It's given us the mean values. It's given us some descriptive statistics. The mean for the before one was 6.9. The mean for the after one was 7.87. So just eyeballing the data, that's almost a whole unit of change in this measure of agility, which sounds quite good. The variance is quite close because this value of variance for the before one group is just under 1, and the variance after for the after one group is just above 1. Now I said to you before, one of the conditions for your data to be considered parametric is for their variance to be similar. It's a very vague word, but in some of the literature, some of the textbooks I've looked at, they've said so long as one number isn't more than 3 times bigger than the other, then you can consider it similar. So I'm thinking, okay, that's pretty relaxed, and these two are well within that limit. It's given us a number of observations, so I've obviously made a mistake here. I thought I was picking the first 20, but I went down to row 20. So if I really was going to do the first 20, I'd go back and do it again. I'm not going to do it here because I'm lazy, but it's given us some good descriptive statistics. Then it's also given us, this is amazing, the Pearson correlation coefficient. Notice this isn't the full Pearson test, but that's kind of nice just to have that. Then, okay, it's told us there's a correlation coefficient. You would not get this line on the independent samples. It's only because these were 2 measures on the same person. Gives us the degrees of freedom, which is the number in one group minus 2, exactly the same definition that we saw in Pearson. The t statistic, notice it's minus because of the way it's been done. It's done before 1, take away after 1, so it's gone negative. Don't worry too much about that, but it's just looked at the left-hand tail. It is best to do it a 2-tailed test, and you'll notice that this value is way smaller than 0.05. The critical value for the 2-tailed test here is 2.10. Now Now, clearly, our value of the t-test in terms of magnitude is way, way bigger than 2.101. But you might go, hang on, the critical value for the t-test is a positive number, but our t-stat was a negative number. No need to panic, because when it gives the critical value by convention, it just gives you 1. But you would read that as plus or minus. So here it said it's 2.101, about there, somewhere like that. We've had a value, it turns out ours is negative, but it's right down here, right in that tail. So even though the critical value was stated to be 2.101, we can read that as plus or minus 2.101, depending on the tail we're in. We're in the negative tail, so we might make a comment upon that in our writing. But we consider the magnitude, the size of our t-stat is far, far bigger than the size of the critical value of the t value, and therefore we can see that p is much less than 0.01. I'm just going to pause there for a second. It's okay. Thought I was going to the door and I didn't have to. So I'm pretty much done with the first discussion of the t-test, but I know that you've got to do more than that, and we've only looked at one version. Let's just look at one other version. Let's look at a t-test of, say, gender. Now, this particular one I've set up where you'll notice they're all magically in order. How did I get that? Well, fairly straightforward. Let me just copy everything again, open up a new sheet again, copy it all in, get rid of that. And if I'm looking at, say, gender, well, I don't want that first row. I'm just tidying things up to make life easier for myself. I don't want this top row. I don't even want the device on this. I'm going to get rid of that one just to make it easy for myself. But gender, I do want that. So let me just click on that row and just say sort and filter, A to Z. Do you want to expand the selection? Yes, I do. And you'll notice now that all the females are together, and then after a bit, all the men are together. Now, fine, except I just want to do something. I want to select that top row, hit Control-C, and then go down to where the males start. Just looking ahead to when I run the t-test, click on that row, right click and put Insert Copied Cells. And then I've got headers for both male and female, so I know what I'm doing. Okay, fine. Now, I've been lazy. I've not worked out the variances, or I could go back and think about it, but instead I'm just going to go straight to the data analysis. Now I'm going to look at males versus females, which is no longer paired, no longer dependent. It's no longer before and after. It is, in other words, not a within group study. It is now a between group study. We know that as well, because just so happens in this data set, there's way more women than men in this particular one, and you can have different sample sizes in your two groups for the independent samples t-test. Now, I don't know what the variances are, so I'm just going to assume unequal variances, but I can always come back to this and redo it. So I've got t-test, 2 sample, assuming unequal variances, which I know is the independent samples t-test. Click OK. We've seen this before, so my first range, I've just got to decide who I'm going to do it against. I'm going to say I'm going to look at, say, for men and women, I'm going to look at, say, let's just imagine I want to know if baseline they were similar or not. Okay, so I'm going to say right for the before ones for women. I'm going to have to select them all this time, otherwise I might fall foul. So there's all the women. Click on the next one for all the men. Start with there because I want the label. So I'm just looking at their baseline measures. Think about what you expect the null hypothesis to be, or rather what the outcome will be. Obviously, we hypothesize there to be 0 difference. We want the labels. I'm going to put the output range. Let's scroll to the top, put it there. Before I hit OK, what do you think is going to be the result? Do you think we're going to get a p-value less than 0.05 or greater than 0.05? Are we going to reject the null hypothesis of there no difference between the men and the women, or not? What do you think? Let's find out. Click OK. I don't know what to expect either, to be perfectly honest, but now I can see the case. I can see that p-values for both 1 and 2 tail tests are well above 0.05. In other words, there is insufficient evidence to reject the null hypothesis of difference between men and women baseline measures. This is really important because that means we can look at differences between men and women afterwards. So just get rid of those, and you might tidy up these, but it doesn't matter. We can say, look at the mean value for the men before. Does it give this? Doesn't tell me which is the men and which is the women. Oh, it's because I didn't put that there. Oh, hang on. Yeah, it doesn't tell which is the female, which is the men. Yes, it does. I can work it out. There's far more women than men. So this 6.96 refers to the women. This 6.95 refers to the men because there's a lot less men. I'm confident to say, look, eyeballing it, those two values are very, very close. The variances are also very close. But the killer thing here was that the P value, the probability of the difference between a fluke, well, it wasn't a fluke because he's 0.95. In others, there's every chance to say they came from the same population, we're fine. That's not very interesting, but an important step. Let's do one other. I want to look, now that I've established that for group 1 or rater 1, the befores were about the same, I want to now look to see if there's a difference afterwards as well. So I'm going to look at the after group. So go into data, go into data analysis. I promise you is my very last one. Obviously, I could have assumed equal variances now, couldn't I? But let's do that. Let's assume equal variances. You'll do a bit more work than I've done on this one. So I'm now going to look at after 1. So I'm going to pick all of those guys. Okay, and then for range the second variable, I'm going to do after 1 again for the men. You can see how I absolutely had to sort my data alphabetically, otherwise I would have really struggled. My variance, sorry, my hypothesized mean difference is 0. I want the labels. I want to keep 0.05. Let's put the output range. Let's put it underneath about here. Click OK. See what we get. I think there's a fair chance there might be a difference. Let's see. No, there isn't. You see, the women after their change, by the way, this is independent of device, their change was 7.83, the men were 7.81. There's a subtle difference between the men and the women. The women seem to have a greater, very small greater, but greater nonetheless, change in their measure of agility. Again, we can say the variances are similar, but the p-value, the two-tail one, the one that I'm interested in, 0.916, again, there is insufficient evidence to suggest that gender has an impact or is an influencing variable regarding whether your devices have a greater impact on one or t'other. Now, obviously, we've got to do far more exploration and want to look at the devices, and I'll leave that for you to do. But what I've covered today, here and now, one very awkward exercise, the Pearson correlation, and I've let you know a little bit about why we run it, the background information, this idea of the parametric versus non-parametric data. This is something you're going to have to do some further reading on your own terms. I'm hoping there's some slides that that the team have given you on that. And then we looked at another part of that flow chart, which was the t-test, and you can see we're only sampling a small amount of the possible tests out there. In fact, this particular flow chart is only a very small amount of the tests that are out there. And then we went through and did the t-test, which was far, far easier. So I'm hoping it was done in a way that you can stop and pause and click along, because it is absolutely crucial that you train on the data that you've been given from Moodle so that you can then check that it is going to be you're getting the same answers that they have, because on Moodle they understand they've given you the answers. And then and only then, when you are sufficiently trained up on it, then you take the data that they give you, which is a bit individualized for your summative part, because then you'll have a greater level of confidence. You'll have done some training, so it's less alien to you. And also because you've trained, you've ironed out, as I had to do when I was learning this the other week, as to how the hell do I do this. And I went onto YouTube and found out various things, discovered some workarounds when this idea of your data being contiguous, that tripped me up and sent me down a rabbit hole. But at least I got there in the end. And of course, in any report, you report the logical steps, not necessarily your mistakes. It's not a question of just stating your answer, but saying what the answer means, using sentences like there is insufficient evidence against an old hypothesis, or there is strong evidence, or there is very strong evidence. Make sure you promote and demonstrate your understanding of as many steps as you can. The key one, I think, being the p-value and how we interpret it. But I think you can also in a position to make statements to demonstrate your understanding about this idea of correlation and the correlation coefficient. Okay, I'm going to stop record. So I'm going to stop sharing there, and I'm going to wish you all the best, and I'm going to stop the recording as well. And I'll be seeing you guys very soon anyway. But all the best and take care. I hope this was quite useful. Cheers then.